Dear students, so we just discussed the interaction of different types of radiations with matter, like heavy charged particles, alpha protons, light charged particles, or fast electrons, beta particles, the gamma rays, and neutrons. These are the types of radiations that one will be encountering while working in a radioactive area. So this interaction of different radiations with matter helps in developing detectors when you want to choose a detector for a particular radiation. So that knowledge will help in understanding the principle of different radiation detectors. Before we go to the actual detectors, different types of detectors that we will be discussing in this lecture, I want to discuss the basic principles of radiation detectors. So how do we get a signal from a detector? Detector will sense the gamma ray or the alpha or beta or neutron. So how do we get the signal from detector? That is what we try to understand. So all of you know that this Henry Becquerel discovered radioactivity using simply a photographic plate. So in essence, a photographic plate also is a detector. One of the oldest detectors is a photographic plate, but that will give you a qualitative picture. So when we want to go for quantification of radiation levels, we use more advanced detector systems. And so the basic principle of detection of radiation is collection of ion pairs. If you recall your discussion on the interaction of heavy charged particles, the heavy charged particles cause ionization. It can also cause excitation, but the ionization will give you ion pairs. And if you collect the ion pairs, you can detect the signal. The electrons also give you ion pairs. Similarly, the gamma ray by secondary means, it will give fast electrons by photoelectric effect or even Compton scattering or pair production. The neutrons also give rise to heavy charged particles by way of nuclear reactions. So the net result of all types of interactions of this ionizing radiation is the production of ion pairs. So if a radiation is going, it will give, suppose let us say alpha plus A is the, let us say atom, then alpha plus A plus, this is ionized, and there you have an electron. So if you can collect this electron and positive ion at the respective electrodes, then you can get the signal. So this is a schematic of a detector. If you collect the electrons at the anode and the positive ions at the cathode by applying a potential at the anode, and so you essentially are charging the capacitor. The electrons will be charging the capacitor, and when capacitor is fully charged, it can discharge through a load resistance R, and the discharge of the resistor you can measure by in terms of a potent voltage or a current. So you can use a detector in current mode if you put a current emitter here, or you can put a voltmeter, you can use in a pulse. So we will discuss both the mechanisms and see also their merits and demerits. So when you measure the current in this circuit, then whatever charge was created by interaction of radiation with matter is the total charge. What is the total charge? So if you suppose you have so many alpha particles coming, okay, so you will have a large number of, what we will say 1 MeV gamma ray. So it will be giving 1 MeV. How many ion pairs will produce? W. So this is W is the energy required to produce 1 ion pair. So electron volt, 1 MeV. So it will be number of ion pairs. So these ion pairs are collected, and that's why essentially you are collecting the charge. That is what this charge is. Now when this charge is discharging through an emitter, then capacitor is discharging through an emitter, you see the current flowing in the circuit. And what you see here in the time domain, you see the current it will be rising, become flat and come down. So one event will be like this, and then there will be several other events. So multiple events will lead to a flow of current in the circuit. And because of that, since there will be a constant current flowing in the circuit, this this mechanism of current mode is not used in the counting of the radioactivity, but it gives you the gross activity level. Like you have a survey meter in the laboratory, just you want to know what the level of radiation, you can use for gross activity counting current mode. Because it is giving you a current level. How many microamp, how many nanoamp, how many milliamp, that tells you that this is the level of radiation. But if you want to count the activity, how many counts per second, quantitatively you want to know, then you require pulse. So you need to shape the pulse. So what do? Whatever charge is produced, Q, you get a potential voltage at the voltmeter, Q by C. So the maximum that voltage will go is depend upon the Q upon C, the capacitance of the circuit. Actually, this capacitance is not only this capacitor, but the detector system also will have its own capacitance. The net capacitance of the detector system is involved in determining the voltage. So the voltage will rise, go to maximum, and again fall down. So this is the V max. And the rise and fall will depend upon the C and R. This is called CR circuit. In fact, the detector systems have a series of RC circuits, so that you play with the circuitry to get a proper signal. Essentially, we want to get a voltage signal. If you see in the oscilloscope, the voltage signal will be like this. It will rise and fall down, and it should fall down before another event comes, so that they can be separated, and so you can count. So we will discuss about the dead time and all. So different individual pulses are counted in the detectors in the pulse mode, and that pulse mode then is used for event by event counting. Each decay you can count separately in the pulse. So the detectors actually are operated in current mode and pulse mode. Some detectors are used in current mode also, like survey meters, where you are interested in only gross activity level. But whenever you want to measure each event separately, then you use a pulse mode. So this is a block diagram of a radiation detection system. You have a detector. It can be a material, it can be gas, solid, liquid, and you have to apply some potential somewhere, because the charged particles have to be collected at anodes and cathodes. So you apply the high voltage at the anode, and then once the signal is coming, the Q, the charge that is collected, you have to get a signal. So the preamplifier does the job of getting a voltage signal or a current signal from the detector system. And the preamplifier actually just giving a initial signal which have a low output impedance. Normally, detector output impedance is very high. It will get attenuated. So you use the preamplifier to decrease the impedance of the output signal, and subsequently you can carry to long distance, and then there is an amplifier which will amplify the signal to a measurable range of 0 to 10 volt or whatever it is. And these pulses are then fed to a counting system, multi-channel analyzer. You have 4,000 channels, or you can timer scaler. You can count in the scalar mode, or you can count you can generate a spectrum in the multi-channel analyzer called MCA. So this is a schematic of a particular detector system. You have a detector material. We'll discuss the details of detectors separately. You need a high voltage, you need a preamplifier, amplifier, and the multi-channel analyzer or scaler. Now, whenever we want to set up a detector system, we should make sure that detector is functioning in a stable manner. The settings of the detector are proper, and so that is why we need to generate this counting curves and plateau. So counting curve and plateau means what? Whenever you are counting, detector is giving you proper results. So there is a quantity called gain. Gain means your amplification factor. So in the amplification, what is the extent of amplification you have to do so that you're counting the signal and not the noise. So I try to illustrate this using this figure here. What I have done here, the gain is like 1, 2, 3 different types of gain, the pulse height. So here it is a pulse height distribution, PhD. So you have a time, the voltage versus the counts, the dn by dv, number of pulses of a particular height. Now, what happens initially, suppose you have got a low gain in the amplifier, then, and you put a threshold in your timer scaler, or a multi analyzer, you have a threshold, let us say 1 volt. Any pulses above 1 volt will be counted. It is below 1 volt, it will not be counted. So this is the threshold for, let us say, 1 volt. So anything beyond this only will be counted. Now at low gain, you can see the noise and the pulse both are below the threshold. So you will not get anything. No counts. So this is the gain versus counts. Then you slightly increase the gain, G equal to 2. And now you can see there is a, the pulse is stretched to the higher pulse height. But still you see some part of the pulse is still below the threshold. So you will get this rising part somewhere here, but not a complete, all pulses are not above the threshold. Then you further increase the gain to the third one, and here noise is below the threshold, but the actual all the pulses are above the usual above the threshold. So this is what is the plateau. And if you further increase the gain, then you will find even the noise will go beyond the threshold, and there will be a rise in the. So this is the plateau region where you have to set up, do the settings. You can operate at this particular gain. In many detectors like Geiger-Müller counter or sodium iodide thallium, you can change the gain of the detector system by high voltage itself. So many a times in GM counter, no, instead of gain, you change the high voltage and set up, find out the high voltage at which the system is stable. So this plateau and counting curves are actually used in the GM counter very routinely to set up the high voltage which you have to apply so that the detector system is functioning properly. So counting curves and plateaus are very important for setting up a detector which will give reliable results, and it will be more stable system. Another important property of detector is the energy resolution. I have discussed the general property of detectors so that we don't have to repeat it every time. So what is the resolution, energy resolution? So a source may be emitting different radiations like different gamma rays or different energy. Whether the detector can resolve those, that will depend upon the energy resolution. So the ability of a detector to resolve nearby peaks we call it the resolution, energy resolution. Just to illustrate here, suppose there are two peaks, 1 and 2. These two peaks are nearby. So if our resolution is good, they will appear as separate peaks. But if the resolution is bad, it can appear like this also. So it could be like this, or it could be broad. So bad resolution and good resolution. This is what we want to mean. So you have to see that the resolution is low. So when you say better resolution, the R value. The R value, how it is defined? R is the resolution in percentage. So if I should this normally when you see the pulse height spectra, they will appear like a Gaussian or a single peak, and the full width of half maximum of a Gaussian. So FWHM, when the counts are become half, the width at that time is called full width at half maximum upon the mean value of the pulse height, FWHM upon H0 into 100. So they have the same unit, this and this have the same unit. It's in terms of percentage. So this is how we define the resolution. So lower the value of R, better is the resolution. So FWHM has to be low as possible. So now let us go a little more details of the how do we define this resolution and how we can improve this resolution. So when the radiation is falling on a detector system, we cannot define a priori how many ion pairs will be created. Though we say E by gamma, E by W is the number of ion pairs. Every time a single energy photon interacts or the alpha particle interacts, it will not give the same value of N. Though energy is constant, W value is actually average energy. So N is not constant. So this is a statistical process. You will say random fluctuation in the number of ion pairs. So you have a large number of atoms in the material, and so you have what you follow is the Poisson distribution. The probability of interaction of the radiation in the particular atom is very small. So we follow the Poisson distribution whenever the probability is very small and the ensemble size is very large. For a Poisson distribution, the second moment, the variance is equal to the mean. So take the mean as the number of ion pairs that are produced, N, then the variance is equal to mean. and variance means the variance is square of the standard deviation. So sigma will be root of mean. So sigma will be root of mean. That means the fluctuation in the, so it will not be sigma, it will be actually 2.35 sigma for a Gaussian. The fluctuations in the pulse height are related to square root of the number of amperes. So if you want to have a better resolution, go for a high number of amperes or low WL. So that consequences we will see subsequently. So for a Gaussian, the WHM is given by 2.35 into the sigma. You can derive from the full Ritter half maximum how it relate to the standard deviation of a Gaussian. So the R now resolution will be 2.35 sigma WHM upon H naught. H naught is the number of, actually it's a proportional number of amperes, so N, and sigma is root N. So you can convert this in terms of root N upon N. 2.35 root N upon N, where N is the number of amperes formed. And so you can now see that resolution, it depends upon, is equal to 2.35 upon root of N, where N is the number of amperes formed. So higher the number of amperes, better is the energy resolution. This is how the resolution, when we discuss different detectors, you will find that the resolutions are different because of the number of amperes that are produced. Another important property of detectors is the detection efficiency. How efficiently the detector can count yours, how maximum counts you can count. So the radioactive sources, they will be emitting the radiation in all possible directions in 4 pi. Though even if you put a collimator, then we are losing the radiations emitted in other directions. So isotropic emission of radiation is the property of radioactive sources. They are emitting in all directions. But your detector has got a finite dimension. So if suppose you have a cylindrical detector having a radius r and at a distance d from the source. So there is something called the geometrical factor. What fraction of the radiation is falling on the detector? That is called the geometric efficiency. And out of that fraction, whatever is falling on detector, what fraction is being counted? That is called the intrinsic efficiency. And the product of the two will call as the absolute efficiency. So we'll go in the reverse direction. Geometric efficiency is the solid angle subtended by the detector at the point is omega upon 4 pi. And this omega upon 4 pi can be written in terms of the area of the detector surface into surface area of the sphere 4 pi d square. Because this detector can be considered as the part of this area of a sphere. So like, you can have a sphere on this surface, you have a small portion is covered by the detector. So pi r square, this is the fraction covered by the detector. So that is called the geometric efficiency. It becomes r square upon 4d square. So you can play with the geometric efficiency, have a large area detector, bring it close to the source and so on. Then out of this, whatever fraction is reaching the detector, what fraction is counted? That is called the intrinsic efficiency. Intrinsic efficiency, number of counts upon number of quanta incident on detector. Because every radiation that is falling on detector may not be counted. So there may be other processes or radiation may escape. So that is called the intrinsic efficiency. And the product of the intrinsic efficiency and geometric efficiency is called the absolute efficiency. So absolute efficiency equal to intrinsic efficiency into geometric efficiency. And so you can in fact call absolute efficiency as number of counts in the detector system upon number of quanta emitted by the source. So suppose it is emitting 100 counts per second, 100 photon radiation per second. Out of those 100, how many are counted by the detector? That is called the absolute efficiency. So in practice, we will be using absolute efficiency. You can have a standard source and find out how many counts you are getting. But it's product of two quantities, geometric efficiency and intrinsic efficiency. Geometric efficiency depends on the geometry of the detector system. Intrinsic efficiency depends on the detector material. So, or even it can depend upon the energy of the radiation. So when we count the activity, we say counts per second. In the peak, suppose you have a peak like this, take the counts. This is the energy versus counts. So this area will be the counts, the counter for a particular time divided by the time, we call the counts per second. And so, but it is not necessary that all the disintegrations are being converted into counts. So there will be, suppose it is emitting certain photons, so efficiency is taken care of, the what fraction is actually counted. So if the disintegration per second, suppose you have got, let us say activity is A0 into efficiency equal to activity. So initial activity, this is the source activity and this is the counts. So you can, if you know the efficiency, if you know the counts, you can find out the absolute efficiency. A0 absolute activity, A upon efficiency. So if you know the counts per second, you know efficiency, you can find out the disintegration per second. So this efficiency is a very important property of a detector. Now comes the counting statistics. So when you are counting a source, you should know for how much time you should count, because there is a limitation on the time also. So for that, let us discuss this in more detail. So essentially the errors, the uncertainty in the numbers dictate for how much time you need to count. So radioactivity, we have already discussed. Activity equal to n lambda. How many atoms are decaying in 1 second, atoms per second? It's called number of atoms into the probability of decay in 1 second, lambda. So again, going by the the probabilistic aspect of this, number of atoms in a sample can be very, very large. If you take a gram, you can be close to Avogadro number. If we, and then the lambda decay constant is a very small quantity. So whenever you have a very small probability of decay and very large sample size, the decay follows a Poisson's distribution. And so for large number of atoms and a small decay probability, we use Poisson. So counting of the radiation in a detector system will follow Poisson's distribution, for which the variance is equal to the mean. That means if you have a single counts, you counted the sample and you get some number n, from that itself you can find out the uncertainty in them. So suppose you get n counts in a detector system, and so you have only one value. How do you find out the uncertainty? Use this formula. So standard deviation sigma equal to root of n. So that is how you get the uncertainty in the counts. So just let us take an example that if suppose you get 100 counts in a detector system, then sigma equal to 10. So uncertainty will be, error will be 10 by 100 into 100, 10%. But if you count for 10,000 counts, uncertain sigma is equal to 100, the error on that will be 1%. Okay, 100 upon 10,000 into 100, 1%. You can see that by counting, by accumulating more counts, you can decrease the uncertainty in your counts. So that is what dictates for how much time you should count a sample. If you want 1% uncertainty, and then you can count for 10,000. You accumulate 10,000 counts. So your time, counting time, is governed by what is the uncertainty that you want to achieve. So many a times, you have sample will have, your detector system will have a background also. So when you are counting a sample, it will also have background. So you have to subtract the background. Without the sample you count, you get background. And so the net count will be gross count minus the background. So you put the sample, you get a count, you remove the sample and you just count without sample or background. So net counts equal to gross count minus background. And so correspondingly the uncertainty is sigma n square will be sigma g square plus sigma e square. So they have their own uncertainties. So the errors are additive. Though you are subtracting gross count minus background, the errors are additive. So if you have, let us say, background equal to background, gross count is, let us say, 1000 and background is 900, net count is equal to 100, but error will be 100 plus 900 square root of sigma n. Sigma n will be 100. This is the error on the g plus 900 and square root. This is the sig. So if the background is high, the error on the numbers is very high. So you have to reduce the background to get more reliable results. These are the things one has to take care when counting. And the last property of detectors is the dead time. Dead time is now when a detector is processing a particular event. For that event, it cannot process another pulse. So during that time, while it is processing one pulse, it is dead to receive another pulse. So essentially, the dead time is the minimum amount of time which must separate two events so that they are recorded as two separate events. So this essentially the dead time is the time required to process a pulse. During that pulse, if another pulse comes, that may not be or may be counted. That depends upon what type of system you have. And this happens when the system has got high count rate, then there will be some impulses will be lost. So the dead time losses are important. So that tells you what will be the sample count, what is the activity. Suppose you put a 1 millicurie sample, then for 3.7 or 7 becquerels, you cannot count. So you require very small quantity, less than a microcurie to count your sample. So I will just try to explain. There are two models of dead time, parallelizable and non-parallelizable. That means, see, there is a train of events. These are the pulses coming in the detector system, and for each pulse you require certain time to process the pulse. So this instead of this, if you recall this, we have shown time versus voltage, Q by C. So this is a voltage signal. I am showing a logic signal, square pulse. Now I have shown the 6 events are coming in the detector, spaced by the time in different manner. So here this pulse is counted. This pulse, before this pulse is over, another pulse has come. And here 2 pulses have come. So one after one more, 3 pulses have come. Depending upon whether it is parallelizable mode or non-parallelizable mode, you will get different events in the detector system. In the non-parallelizable mode, in the second pulse, when this is coming, the second pulse is not counted. You see here. Whereas this here, there are 3 events, they are counted as 2 events. Because after this, the detector is available to detect the other pulse. Whereas in the parallelizable mode, you get 1 event here. This is again 1 event, and this whole thing is coming as 1 event because it is parallelized. So this detector is seeing this whole thing as 1 event. So you get 3 events, you get 4 events. Actually, there were 6 events. So that is the different meaning of the parallelizable and non-parallelizable mode of dead time. And depending upon the type of model for dead time, there are the observed count rate. So the N is the true count rate. How many count the sample is emitting, event sample is emitting, how many observed, M is observed count rate, and tau is the dead time, system dead time. So the relationship between the observed count rate and the true count rate for parallelizable are M equal to N e raised to minus N tau, and for non-parallelizable is N equal to M upon 1 minus M tau. So you can use, the detector system will follow either parallelizable or non-parallelizable. One has to do an experiment to see what kind of model the detector follows. So just to see how this one can determine the dead time of a detector system. So for this purpose, people follow a two-source method. Two-source method, let us say one is S1 and S2. So you count a source, one source separately, you count second times S2, and then you count S1, S2 together. So when you count S1, S2 together, there will be losses in the counts because the count rate has increased. And so this can be made use of in finding out the dead time. And this D1, D2 are the dummy. Dummy means when you are not putting any sample, you put a dummy source. There is no activity in that. That is a dummy source. So you have now 4 sources, S1, S2, D1, D2. D1, D2 are the dummy D values. These are D sources. The dimensions are of a semicircle. And so you can put, so N1 is a true count rate for N1, sample 1, source 1, N2, true count for source 2. And when you put them together and count, you get the N12, true count rate of the combined source, and there is a true background count rate. But actually what you get is not N, you get M. So you can try to analyze N12 minus 12, B, NB, the background, you subtract the background, N1 minus NB plus N2 minus NB, the true counts, no? So you can arrange N12 plus NB is N1 plus N2. This is not the count, what you are counting, what you are the true activity counts of the sample. Now you apply the non-parallelizable model, N12, M12 upon 1 minus M1 tau. So all you can replace by the M value. So this is an equation where you are observing the counts. M1 is when you have put this one, M2 is when you put the S2, and M12 is when you put both of them together, and D1, D2 when you put background is called MB. So from this you can solve this equation to find out the tau. The tau comes in terms of x, y, z, where x equal to this term, y equal to this term, and z equal to this term. They all depend upon the M1, M2, MB, and M1. So you can actually just calculate the dead time by in the non-parallelizable model for the detector system. Particularly, there is an experiment in the GM counter, and if you happen to use a GM counter, one can use this setup two source method to find out the dead time of a Geiger count. This is a very huge general experiment for the radiochemistry people that determine the dead time of a GM count, and that comes to about few hundreds of microseconds. So today, what I try to show you the different properties of the detector systems, and these properties will be used when we use the different detectors. Then we will use the terms quite often in our discussion. So I'll stop here, and next time we'll discuss the different types of detectors. Thank you very much.